Hello, hello.
Hello.
Yeah, can you hear me?
Yes, sir.
You have to be on time.
Yes, sir. Yes, sir.
Okay, we'll start with calculus, and the first topic here is functions. So we'll go in the normal sequence: functions, limits, continuity, differentiability, and like that we have to learn. Okay, so how much do you know about functions?
Sir, function is a machine. Is a machine that we put some input, it gives some output.
Basically, the idea is that there is a connection between elements of one set and elements of another set, right? If you say
Yes.
this is set A and this is set B, if there is some connection between elements of this set and elements of the other set, then we can say that it may be a function. So we have to understand how to describe this sort of a connection, right? So first
Yes.
of all, let there be two sets A and B, be two non-empty sets, non-empty sets. So we'll first define the idea of Cartesian product. What is A cross B, or Cartesian product of two sets? Do you know what Cartesian product is?
Yes, sir.
Basically, it is the set of ordered pairs where the first element is from set A and second element is from set B, right?
Yes.
So we can make AB such that A belongs to set A and B belongs to set B. So in our example, the ordered pairs will be like this: A1, then A2, then A3, then A4, and similarly B1 till B4 and C1 till C4 and D1 till D4. Do you understand what I have written?
Yes, sir.
So the set of ordered pairs is called the Cartesian product of two sets. And if this element has m, this set A has m elements and this has n elements, then the number of ordered pairs here is mn.
Yes.
In our case, m and n was both 4, so it was 16 ordered pairs would have come, right?
Yes.
So this
Yes.
is your Cartesian product. Why are we defining Cartesian product? Because using Cartesian product itself, we can define both relations and functions. So let's say you have a Cartesian product A cross B is equal to the set of ordered pairs such that A belongs to first set and B belongs to second set. Here you should know this symbol. This means such that.
Yes.
And this is the set of ordered pairs such that these conditions have to be true. So if you have that situation, let's say they take a smaller set A, B, C, and this is 1 and this is 2. So only 6 elements will be there in this Cartesian product, right?
Yes.
Now, how many subsets are possible for A cross B? How many subsets of A cross B are possible? So first of all, you should realize that A cross B, the number of elements of A cross B is mn, right?
Yes.
So if the number of elements of a set is n, how many subsets are possible for that set?
2 raised to the power n.
Right. So for subsets of A cross B would be 2 raised to the power mn, right?
Yes.
So there are many subsets of A cross B. 2 raised to power mn. In our example, it will be 2 raised to the power 6. Because when you make
Yes.
a subset, you have a choice of whether to include or whether to exclude one particular element, right?
Yes.
So there are two options for each element. Here there are 6 elements. So 2 into 2 into 2, 6, 2 power 6 options for all of them, right?
Yes. Yes.
That's how you can make a subset. Now what we
Mm.
will say is any subset of A cross B is a relation between A and B. Do you understand what I'm saying?
Yes, sir.
So actually there are 2 power 6 subsets possible, and you can say that any of those subsets can be called as a relation between the two sets. For
Mm.
example, let's take one particular subset, subset 1, which is A1. That's all, right? Subset
Yes.
2 could be A1 and A2,
Mm.
right? Subset
Yes.
3 could be A1 and B1,
Okay.
right?
Yes.
Obviously, there are many other subsets possible. There are many other subsets of one element, two elements, three elements, till 6 elements you can have subsets, right?
Yes.
2 power 6 is basically 64. So I'm going to just list down 2, 3 of them, right?
Yes.
All of these are telling us that there is a connection between the two sets, and you can say that the first subset is this, and this is called a relation, relation S1,
Mm.
right?
Yes.
Because it is a subset of A cross B, therefore it is a relation, right?
Yes.
The second subset would be this one and this one, right?
Yes.
The third subset would be uh, A1 and B1. So B also we can connect to 1, and we can call that is the third relation, right?
Mm. Yes.
So relations are pretty simple. Relations are just subsets of A cross B, right?
Yes. Yes.
So now what are functions? So functions are special subsets, special subsets of A cross B, and we will define what we mean by special. So
Mm.
this is A, this is B, this is C, this is 1, this is 2. Now, not all subsets will be called functions. All subsets are relations, but not all of them are functions. Okay.
Okay.
So, what is special? There are two rules that have to be followed. All elements of set A must be linked to something in set B, to an element in set B. And the second rule is a single element of set A can be linked to only one element in set B. Do you understand what I'm saying?
Yes, sir.
So remember that when we try to make relations, we were taking any subsets, right?
Mm.
This
Yes.
was one subset. We can make another subset like this, simply this. Another subset could be A1, B1, C1. Another subset could be A1, B2. Another subset could be A1, A2, B1. And another subset could be A1, B2, C2. Do you understand? I have listed out 6 subsets.
Yes, sir.
All 6 of them are relations, right?
Yes.
But all 6 of them are not functions, okay?
Yes.
Because they don't satisfy the two necessary conditions to be a function.
Mm.
So what
Yes.
is the first condition? All elements of A, B, C must be linked to something.
Yes.
For example, you can see in relation 1, only A is linked and B is linked.
Yes.
But C is left alone, right? Nothing is there
Yes.
about C. So
Hmm.
this is not a function.
Yes.
Similarly, this will not be a function,
Yes.
right? Again,
Yes.
we can say this is not a function because it doesn't satisfy the first rule.
Yes.
All the elements of the first set have to be linked to something, right? This is
Yes.
also not a function.
Yes.
So four of them are not functions because they don't satisfy the first condition.
Okay.
Notice that all of them are still relations, right?
Hmm. Yes.
Second rule is a single element of A can be linked to only one element in set B, which
Hmm.
means you can't have something like A is linked to 1 and A is linked to 2 also.
Yes.
That is not allowed. One single element of A can only be linked to one thing in B, right?
Hmm. Yes.
So for example, if you see here, A1, B1 and C1, this is allowed. Why? Because each of A, B, C are linked to 1, right?
Yes.
It's not like one element of A set is linked to multiple outputs, right?
Yes.
So this satisfies first condition also and second condition also. This is a function.
Yes.
Do you understand what I'm saying?
Yes, sir.
Similarly, R6 is a function, right?
Yes.
Because A1, B2, C2, right?
Yes.
So it is covering all the three elements of set A and also each element has only one output,
Yes.
correct?
Yes.
You could not have a situation like this. Suppose you change R5 a little bit and R5 you add a term C1, right?
Hmm.
R5 will still not be a function.
Okay.
Why? Because
Sir,
you have
because
these
A2.
two, right?
Yes.
There is A1 and A2 that is not allowed in a function
Hmm.
because you cannot have one single input and two possible outputs, right?
Okay. Yes.
So this is the set of possible inputs, right?
Yes.
And these are the set of possible outputs, correct?
Yes. Yes.
So that is the meaning of function from a set theory perspective. And now we can define certain terms like domain, codomain, and range. So let's say we have a function from A to B, A, B, C, 1, 2, 3, 4. Now let's say we have a connection like this. Notice that it is okay if some element in set B is left with no connection.
Yes.
That is allowed. What is not okay is if there was a D element here which was not connected to anything.
Hmm. Yes.
Do you understand what I'm saying?
Yes, sir.
Those two rules have to be clear in your mind. Then only you can identify what is a function or not. Right?
Yes. Yes.
Okay, so here we will say that set A, which is the set of possible inputs
Hmm.
to the function, is called, it is given a name and is called the domain of the function. Domain of the function, right?
Yes.
And set B is the set of possible outputs of the function. And this set is called the codomain. Okay.
Yes.
So there is a domain which is set A, codomain is set B, right?
Yes.
But there is a difference between what is called codomain and what is called the
Hmm.
range of a function. So notice here that it is possible to have a set B where some element was not connected to an element in set A, right?
Yes.
For example, this element is not being connected to anything there, right?
Yes.
So 4 was in the set of possible outputs, but was not an actual output. Do you
Yes.
understand what I mean?
Yes, sir.
It could have been that 4 was an output, but in reality, for this function, it is not an output, right?
Yes.
So we will say range is the set of actual outputs of a function. In this case, we can say that codomain is the set 1, 2, 3, 4, whereas range is the set of actual outputs, which is 1, 2, 3 only. Do you understand what I'm saying?
Yes, sir.
So it is possible that the range of a function is slightly lesser than the codomain. So you can always say that range is a subset of the codomain.
Okay.
This symbol stands for is a subset, right?
Yes.
In some situations, it could be that range and codomain are equal. Both of them are equal. It could be that we didn't have the 4, right?
Yes, sir.
If 4 was not there, then codomain set is also 1, 2, 3 and range set is also 1, 2, 3, right?
Yes.
So it is possible for range to be equal to codomain, but it is not necessary.
Yes, sir.
Do you understand what I'm saying?
Yes, sir.
Okay, then we will start looking at some basic things like types of a function. So we will understand the 4 types of functions. This is an important concept. So first concept is 1, 1 versus many 1. So the name itself suggests what it means. 1, 1 function will be functions where one single input is connected to, there is a unique output here. So what I mean by that is B will be connected to 2, C will be connected to 3. This is a 1-to-1 function,
Okay.
right? It
Yes.
is not a function of this type. It is possible functions could be like this. A is connected to 1 and B is also connected to 1 and C is connected to 2, right?
Yes.
You can see here that many inputs are giving the same output, right?
Yes.
So this is a many 1 function and this is a 1, 1 function, right?
Yes.
So when you have a 1, 1 function, you cannot have a situation where multiple inputs are giving the same output, right?
Yes. Yes.
So another way to say it in terms of algebra is if f of x1 is equal to f of x2 implies x1 is equal to x2, then f is a 1, 1 function. Do you understand what this statement is?
No, sir.
So the statement says, what do you not understand?
Sir, how that x1 and x2 can be equal because the function can be different, no, sir? F of x1 and f of x.
I am saying f of x1 is equal to f of x2 if that is given to you.
Yes.
The outputs are equal.
Okay.
If that implies that x1 is equal to x2, this
Yes.
statement, the meaning of the statement is that if the outputs are equal, means the inputs are also equal.
Okay.
Then the function is 1, 1. You understand or don't understand?
Yes, I now understand.
For example, if somebody told you that in this function, when f of a, if f of a is equal to f of b implies a is equal to b. That means whenever f of a is equal to f of b, the only way it can happen is the inputs are also same.
Yes.
That is not true for this function, by the way, because f
Yes.
of a is equal to f of b, but inputs are different, right?
Yes.
So when you see examples, so for example, let's take a typical 1 function, f of x is equal to x cube. Now, how can we show that it is a 1 function? We can show it by saying that we'll use the condition. If it is 1, we will show this condition. F of x1 equals to f of x2 should imply that x1 is equal to x2.
Yes.
Do you understand the meaning of this symbol?
Yes, sir.
So basically, we are saying this is the assumption, and from the assumption, we can prove this, right? Do you
Yes, sir.
understand what I'm saying?
Yes, sir.
If this condition if this happens, that from this assumption we can prove this, then we can say that it says 1, right?
Yes.
So let's try it out. F of x1 is equal to f of x2. So you'll say f of x1 is what? x1 cube is equal to x2 cube, right?
Yes.
So from here we can say x1 cube minus x2 cube is 0. And then we can take factors like this, and then x1 square plus x1 x2 plus x2 square, right?
Yes.
Now, if you think about this quadratic, we can prove that this quadratic will never have real roots. For example, how can we prove that? We can say that this is x1 square plus half into x1 into 2x2. Okay, 1 second. We can do it like this. 2 into x1 into x2 by 2, right?
Yes.
Plus x2 square by 4 plus 3x2 square by 4. Do you see that it's the same thing as this?
Yes, sir.
I have just written x1, x2 like this, and I have
Yes.
split this into two parts.
Yes. That becomes a perfect square.
So here this can be written as x1 plus x2 by 2 whole square plus 3x2 square by 4, right?
Yes.
So it is guaranteed now that this quantity will be greater than 0, because we are not saying x1 and x2 are both 0. Only in that case it will be equal to 0, right?
Yes.
We are not taking the case where x1 and x2 are both 0. So in that case, this quantity can never be 0, right?
Yes.
So the only way you can have x1 cube is equal to x2 cube, this quantity can never be 0. So that implies that x1 minus x2 is 0, right?
Yes.
So from here, we are able to prove this,
Yes.
correct? So the
Yes, sir.
function is going to be a 1 function, right?
Yes.
For example, this is not always necessary. For example, you can say that if f of x was x power 4 plus x square, this function will not be 1, and I can show that it will not be by trying the same condition. Let's try f of x1 is equal to f of x2, right? So we'll
Yes.
say x1 power 4 plus x1 square is equal to x2 power 4 plus x2 square, which means let's bring everything to one side. x1 power 4 minus x2 power 4 plus x1 square minus x2 square is 0. And we can factorize this and take this common. We'll get x1
Yes.
square minus x2 square common, and inside we'll have x1 square plus x2 square plus 1, right?
Yes.
Now this part cannot be 0, not necessary, never be 0, right?
Yes.
So that implies that x1 square minus x2 square is equal to 0. But that implies x1 minus x2 times x1 plus x2 is 0, right?
Yes.
So this means that f of x1 is equal to f of x2 implies either x1 is equal to x2 or x1 is equal to minus x2.
Okay.
So we are not getting just this, right?
Yes.
We are getting another possibility, right?
Yes.
So it is possible that you can have x1 is equal to minus x2, where this f of x1 will be same as f of x2, right?
Yes.
So then Anytime you take an element x, you can also say another element minus x will satisfy the same output will be same,
Okay.
right?
Yes, sir.
So therefore, this is going to be a many one function because it doesn't satisfy the one condition.
Okay.
Do you understand what we have done?
Yes, sir.
So you need to understand the one many one distinction. And the second type of distinction is the distinction between into and onto functions. The difference between into and onto functions. So that can be understood from the set theoretic diagram. So let's say this is the situation A, B, C, 1, 2, 3, and again A, B, C, 1, 2, 3. So if a function is like this is a valid function, right?
Yes.
It satisfies all the conditions of being a function. There is no issue with it, right? It is
Yes.
also a many one function, by the way, right?
Yes.
Do you understand what I'm saying right now?
Yes, sir.
But there is a type of function, there is an element here which is not a part of the inputs, right? Which is not linked to the inputs.
Yes.
So 3 is an element of the codomain which is not connected to any element in the domain, right?
Yes.
So
Yes.
this type of function is known as an into function. Whenever into function is a type of function where range is a proper subset of codomain.
Okay.
This is the symbol for proper subset, which means that range is smaller than codomain,
Okay.
right?
Yes, sir.
Range is a subset of codomain. Range is not equal to codomain. There is an element
Mm.
in codomain which has no pre-image, which has no connection to the domain.
No. Yes, sir.
Do you understand what I'm saying?
Yes, sir.
So that type of function is known as an into function. And if I had drawn a function like this instead, where you can see here that range is equal to codomain,
Yes.
that type of function is called onto function.
Okay.
The condition for onto function is that the range and codomain should be equal.
Yes.
The actual outputs match the possible outputs, right?
Mm. Yes.
So now these four terms you can also combine. You can say many one into many one onto 1 into and 1 onto, right?
Yes.
So these terms can be combined and you should be able to draw the graph of such types of functions, draw the set theory descriptions, right? So if it
Yes.
is many one into, I should have a situation like this. Let's say 1, 2, 3, A, B, C. I should have like this, many one, and into. So 3 is left untouched.
Yes.
Do you understand?
Yes, sir.
If it is many one on 2, I should have a situation like this. A, B, C, right?
Yes.
This is many one, it is also on 2. There is no other element that is left behind with no connection, right?
Yes. Yes.
Then there is 1 into. 1 into would be single connections, but one of them will be left behind. Here, one element will be there, which will be extra, right?
Yes.
At least one, it could be more also, but at least one element has no connection, right?
Yes.
And finally, the fourth kind would be 1 on 2. And here it is guaranteed that the number of elements in both sets have to be same.
Okay.
Do you understand?
Yes, sir.
This is your 1 on 2 function.
Yes.
Is it clear what we have done so far?
Yes, sir.
Okay. Then there are some basic standard types of functions that you might have already seen, like polynomial function. What is a polynomial function? So you have f of x is defined in this way: a0 x bar n plus a1 x bar n minus 1 plus a2 x bar n minus 2, and so on till an, right? Here
Yes.
a0 is not equal to 0, and a1, a2 till an are complex numbers. They don't even have to be real, they could be complex numbers also. Still, it will be a polynomial as long as your n is belonging
Whole
to
number.
whole numbers. So it could be 0, but that will make it a constant polynomial. But it
Okay.
cannot be negative. It has to be 0 or natural numbers, right?
Yes. Yes.
Powers cannot be negative, then it is not a polynomial. Okay.
Okay.
And these can be complex numbers, and this type of function is known as a polynomial function. Then the degree of the polynomial is basically the highest powers coefficient, right?
Yes, sir.
In this case, the degree is n,
Mm.
right?
Yes.
If you think about it, the domain of this function, domain of the function is x belongs to real numbers. Because for
Yes.
any real number, the function is defined. When we say domain, we think of possible inputs, right?
Oh, yes, sir.
So possible inputs will mean, which means like any allowable input, any input that doesn't like destroy the function by being divided by 0 or something, right?
Yes, sir.
But nothing like that is happening here. Any real number can be given as input, right?
Yes.
And the range of this function, you will have to think of the sign of a naught and stuff, and how it is going to be as x goes from minus infinity to plus infinity, right?
Yes.
So it could be the range is also minus infinity to plus infinity, or it could be a smaller range. So right now, without looking at the numbers or without knowing what the numbers are, we can't predict the range. Okay.
Mhm. Yes, sir.
Only once we get a polynomial, we can properly say its range and all. Right?
Yes. Yes.
The second type of function is the rational function. And rational function is basically of the form of rational numbers, but now we have functions. So we have h of x is equal to f of x by g of x, where fx and gx are two polynomials. Fx and gx are two polynomials. Okay.
Yes, sir.
So then this function is your rational function. And here, when you think about it, the domain will be all x such that g of x is not equal to 0,
Yes.
right?
Yes.
Any x will be part of this rational function or will be in the domain of the rational function, except those x's which make the h of x become
Not.
undefined because g of x becomes 0, right? Correct?
Yes, sir.
Then there is the obvious function called the constant function. Constant function is just f of x is equal to k, where k is a real number. K is some constant, right?
Yes.
This function is obviously domain is x belongs to real, right?
Yes.
Any input you give, the output is always k, right?
Yes. Yes.
Range is basically one element, right?
Yes.
Just k.
Yes.
Are you understanding what I'm saying?
Yes, sir.
Then there are functions like logarithmic and exponential functions. So we'll see those as well. Logarithmic function. So have you studied logarithms before?
Yes, sir.
So f of x equals, let's say, log base ax, right?
Yes.
This is your logarithm standard. Now here there are conditions that have to be followed for the logarithm to be properly defined. Okay.
Yes, sir.
So the base, first of all, the base has to be greater than 0.
Yes.
Secondly, base cannot be 1.
Yes.
These are two conditions on the base that have to be followed. Also, the logarithm cannot be defined for any negative input.
Okay.
X also has to be bigger than 0. So
Yes.
basically, whenever you say a logarithm AB, you have three conditions. A is greater than 0, B is greater than 0, A is not equal to 1.
Yes, sir.
Then only you can say that this is properly defined. So here I have defined my log function like this. So obviously the condition on x is that x is greater than 0, right?
Yes.
Because that means then only log will be defined, right?
Yes.
So that gives us the domain. The domain will be x greater than 0.
Yes.
Any x which is x greater than 0 is the domain, right?
Yes.
The graph of this function also can be drawn and it will be somewhat like this. Okay. And
Yes.
this is your y-axis. The graph will go down to minus infinity and will go up to infinity also, but it goes up very slowly. Like it will
Yes.
become infinity near infinity x. Okay.
Okay.
It grows very slowly. It is not rising very fast. Okay.
Yes.
But it is still rising. It's not like it's going down or anything.
Oh,
Okay.
yes.
And this point is the point where it is equal to 0, and that will happen when x is equal to 1. So for
Yes.
x between, see, the domain does not include 0. 0 is not part of the domain. Domain includes all these values and all the other values, right?
Yes.
When the x input is between 0 and 1, the log is negative, right?
Yeah.
But
Yes.
that depends on whether your a is bigger than 1 or not.
Yes.
That is, for a greater than 1, you will have the graph like this. If a
Yes.
was less than 1, the graph will be reversed like this. This is for a less than 1, graph of log ax. Again, this is 1. It is going to be infinity here and it is going to go down to minus infinity at x tends to infinity.
Yes.
So the normal graph of log function is like this. This is just the reverse of it. This is for the case where a greater than 1.
Yes.
Do you understand what I'm saying?
Yes, sir.
You can verify this by using some examples and trying to plot a basic graph,
Yes,
right?
sir.
Then there are exponential functions. F of x is equal to a power x. So exponential functions, the domain is simple. There is no restriction on it. X can be any real number.
Yes.
But here you can realize that the range is quite restricted because the range
0
will
to.
be depending on if a is greater than 0, right? The range
Yes.
will always be positive.
Okay.
A power x is always positive,
Yes.
right?
Yes,
So the
sir.
outputs would be basically anything from above 0. Anything above 0 can be an output, right?
Yes, sir.
The graph of your typical exponential function looks like this. It goes up. When x is 0, the value will be 1, right?
Yes, sir.
When x is very negative, it will tend to 0, right?
Yes. Yes.
And it rises up like this. This is your exponential function. Obviously,
Yes.
you have a different graph if the exponent is between 0 and 1. The graph would be like this then.
Yes.
A is less than 1, greater than 0 in that case.
Yes.
Do you understand what I'm saying?
Yes, sir.
Okay. Then there are two special functions that you should know about. One is called the greatest integer function.
Sir, I have one doubt.
Hmm. What is the doubt?
Sir, you are told that a raised to the power x, so a will be greater than 0.
Right, yes.
Yes. So, sir, what if we take -1 and x should be 3? So it will be possible, no, sir?
What do you mean? -1 and x is be
So
3.
means a raised to the power x, for to be defined, x belongs to any real number domain,
Yes,
and a should be greater than 0.
yes.
So what if we take a is equal to -1 and x is equal to 3? Cube means cube root of -1.
You are asking whether this is a function or not.
No, sir. This will also be defined. No, for you have told a greater than 0.
What do you think I mean when I say it is defined or not? It is defined whether you can call it a function or not. That is the meaning. Obviously,
Yes.
-1 power 3 is a number. It's equal to -1. I'm talking about it being defined on the basis of whether we can call it a proper function or not.
Okay.
Do you understand what I mean?
Yes, sir.
If I do something like this -1 to the power x, now I don't know what will happen when x is not an integer.
Yes.
Do you know what will happen when you do -1 to the power 1.2?
No.
So it will be annoying. You cannot find the values of these. So that's why when we call exponential functions, we take the care that we don't put negative things to the power x.
Yes.
If it was 1.1 to the power 1.2, this can be calculated.
Yes.
If I wanted to find the value of this, I can take log and find the value.
Yes, sir.
But can you do that for this?
No.
So when we are saying it is not defined, it's not defined only because we can't put it as part of my exponential function.
Okay.
We can't take the cases where the a is a negative number and call it an exponential function, because such functions, this will not be defined for, you will not know how to predict its values only. You will not, this is not a properly defined function.
Okay.
That doesn't mean that -1 power 3 is an undefined value.
Yes.
-1 power 3 is simply -1. Do you
Yes, sir.
understand what I'm saying?
Yes, sir.
We here you are not talking about it as a function. You're just talking about what is this. Obviously, you know the value of it.
Yes, sir.
Do you understand what I'm saying?
Yes, sir.
The next two functions are greatest integer functions and fractional part function. These are important to know, and you will see many places where they will come. So fx is equal to greatest integer function of x. This square bracket denotes GIF. And what this means is greatest integer less than or equal to x, right?
Yes, sir.
So for example, if I had to take GIF of 1.2, I would say it is equal to 1. GIF
Yes.
of 2.1 would be equal to 2. GIF of 2.9 would be equal to 2. GIF of -1.3 would not be -1, it will be -2.
Yes.
Because the integer less than this is -2, not -1. -1 is greater.
Yes.
If it was an integer, GIF is same as that integer.
Yes.
Do you understand?
Yes, sir.
The inputs can be any x, domain is x belongs to real. The outputs will only be integers,
Yes.
right?
Yes, sir.
And the graph of this looks like a step type of a graph. At 0, it is 0, and it is 0 till anything till 1. And as soon as you reach 1, it becomes 1.
Yes, sir.
Do you understand what is happening?
Yes, sir.
So
Yes.
this type of step type of graph is your graph of the GIF function. right?
Yes.
Now, fractional part function is related to GIF only, FPF, and you denote it by y is equal to fractional part of x. It is denoted by these curly brackets. And what this means, the definition is x minus GIF of x. So if you think about it, it is going to give you the fractional part between x and its GIF. What is the gap between them, right?
Yes.
You can prove that it will always lie between 0 and 1. The output of the fractional part function is always going to be between 0 and 1. For example, for 1.3, if you calculate fractional part, it will be equal to 1.3 minus GIF of 1.3, which is going to be 1.3 minus 1, which is 0.3, right?
Yes. Yes.
But if you want to calculate it for minus 0.8, let's calculate GIF of negative number, fractional part of negative number. So it will be, again, by definition, minus 0.8 minus GIF of minus 0.8, right?
Yes.
So this is minus 0.8 minus GIF of minus 0.8 is how much?
-1.
So minus 1 is coming from here. So it is going to be plus 1 minus 0.8, right?
Yes.
So this is coming out to be 0.2. So notice
Zero.
that the fractional part value, even for a negative number, is coming positive, right?
Yes.
And it is
Yes.
going to always be between 0 and 1.
Okay.
The domain is all reals. X belongs to real, right?
Yes.
And when you draw the graph will look something like this, and then again like this, and then again like this, and so on.
Yes.
You can check the values and see the graph. It is between 0 and 1,
Okay.
right?
Yes.
So these are some standard functions that you need to know about. Then we have a few more types of functions and some ideas like composite functions and all that we have to do, but that we will cover in the next class onwards. So we have to
Yes.
do signum function, composite functions, and we have to learn what is equality of functions, even and odd functions, and then we'll go into some problems. Okay.
Yes. Okay.
So right now, just revise the theory that we have done so far and try to do some examples and all from your coaching books. If you have your Allen book, you can try to do questions from there.
Yes, sir.
You have the Allen modules for function.
Yes, sir. I have.
So start doing the Allen modules, the beginner boxes, reading the theory from there. Everything that is there in the module, you have to do.
Yes, sir.
And if you have doubts, just mark them. We'll discuss them in the next class. Okay.
Yes, sir.
Okay. Fine. That's it for
Sir,
now.
when would be the next class?
What time are you free on most days in the weekdays?
Sir, after 8 p.m. also and before 3 p.m. also.
So before 3 p.m. we'll do the class. We'll do the class on Tuesday.
Okay.
Tuesday around 1 p.m. That's fine.
Yes, sir.
1 p.m. should be fine, right, for you?
Yes, sir.
So 1 p.m. on Tuesday will be the next class. So read up what we have done, try some examples, see if you are understanding it, and if you have any doubts, just mark it. Okay?
Okay, sir. Yes, sir.
Okay, that's all for now. We'll continue next class then.
Thank you, sir.